Well, congratulations. You've made it through another chapter. Now it's time to review by way of standardized test sample questions. Well, even though this is multiple choice, I think it's easiest to just determine what xw would be, and then pick the expression that corresponds to what we came up with as an answer. Here we have 45 degrees. Now we could use tangents and all kinds of stuff. What we're looking for here is this. See if I can. We want this whole thing, xw. Well, we have these two right triangles, and we know one of the legs and the angles, so we can determine all the sides and angles of the right triangles if we want. All we really need is xz and zw. Well, what would xz be? This is a 45 degree angle. That means this must be 45. And this is an isosceles right triangle. So instead of using tangents or any other trig functions, why don't we make use of what we know? And what we know is that the legs in a 45, I'm trying to say that if the angles are 45 degrees, we know that we have an isosceles right triangle, which means the legs are the same. So xc, we just right off the bat can write that xc equals 5. Now this is a 30-60 triangle. And we should remember that with our 30-60, I'm going to draw a really bad right triangle here. If this is a 30-60 triangle, what do we have? We have x, 2x for the hypotenuse, and x times root 3. So we didn't even have to use our tangents or any of that stuff, did we? Because they were nice enough to give us the two right triangles that we already know all about. In fact, those are the only two, I think, that we can instantly describe just by knowing one of the angles, the 45 and the 30-60. So what would zw be? Well, root 3 times this leg over here, but that leg is 5. So zw is 5 times root 3. And we have to add these up to get xw, so it would be 5 plus 5 times the square root of 3, and that's right here. So we really didn't need much make use of our trig functions because they gave us two triangles that we already know all about. And it's good to keep that in mind, because you can save yourself a lot of time and not have to pull out your calculator and all that by remembering this. And of course, for this, we didn't need it, but this would have been root 2 times 5 for the hypotenuse. Well, now for this one, they gave us the area, which we know is 1/2 BH, where h is the altitude. And in this case, EF would be the altitude. It's perpendicular line to this vertex here. What we want is this length, which is the hypotenuse. Well, B is 40 meters. That's the base here. So what we have to do is set this equal to 400, but we need to insert some numbers here. 1/2 times 40 equals 400, or so we have that this part here, so our same as our altitude, equals 20. In this case, Pythagoras' theorem would probably give us the quickest route to this length here. That's 20 squared plus 40 squared would equal EG squared. So if we lay this out and get our, here's Pythagoras' theorem right here. So EG would be the square root of 20 squared plus 40 squared, which is 44.7. And you know what I did? I forgot to show you that this is actually multiple choice. Although I would have done it exactly the same way. The choices were just a bunch of numbers, so there's no way to know which one to choose without actually working out the whole problem. And if you happen to have this book, the choice was C for 44.7. If not, it's kind of irrelevant. There was just a bunch of other numbers to pick from, and none of them were right. In a case like this, the fact that there are other choices is kind of irrelevant. Just figure out the length of EG, and that's the answer. Then match it up with the one that you see. In some multiple choice problems, there are quicker ways than to actually work out the whole problem. You can eliminate quickly, or you can spot things that would have to work and things that would have to not work. In this case, no. All the other answers are... Well, here's what the choices look like, actually. They just gave you a bunch of numbers. So having these numbers in front of you wouldn't help you work the problem any. Some of them you could discount immediately. The 10 and the 20 you could throw out because the hypotenuse has to be greater than 40. But there's still no way to know which one of these is right without actually working out the problem. Here we'd like to know which expression can be used to find the value of x. That's the opposite side. Well, the sine of 29 degrees would equal opposite over hypotenuse. That's x over 17. That's what we have here, but we have cosine here. In fact, there's not a sine anywhere in this mess. Why is that? Well, what's 90 minus 29? 61. And remember earlier, we pointed out that things like the sine of 90 minus alpha is the same as the cosine of alpha, and vice versa. So we want the sine of alpha, we can take the cosine of 90 minus alpha. I rewrote this according to the way we're actually doing it. The sine of alpha is the same as the cosine of 90 minus alpha, which is the cosine of 61 degrees, equals x over 17. So the correct answer here would be D. Normally, the quickest way would be just to take the sine of 29 degrees, but that wasn't one of the options. And the fact is, the cosine of 61 degrees will work just as well. And here's one. Let's see. A fire station, a police... Gee whiz. Sounds like the beginning of a joke. A fireman, a policeman, and a nurse all walked into a bar. Well, you'd have to Google it. The only joke I know about anybody walking into a bar is one about a bear walking into a bar. It's clean. You can Google it. So what do we have here? They're not in a straight line. Okay. So let's just put 3 little points over here. And say that these are going to be our fire station, police station, and hospital. Now we have to lay them out according to what they're giving us here. Distance from the fire station to the hospital. Let's say this is the fire station. What the heck? And let's see. Fire station to the hospital. So we'll say this is the hospital. And this is 3 miles. And, oh, here we go. Police station to the fire station. That's 4 miles. just call that P, and let's call this F for fire station, P for police. Now we have this one here. This is 3, this is 4. What's this distance here? I think that's what they're asking. Well, actually what they're asking you to figure out is what could not be the distance. Well, we could start by looking at our triangle inequality. The sum of any two sides has to be greater than the other side. So let's say pH here. 3 plus pH has to be greater than 4. So pH is greater than 1. Okay. Well, looks like we're about done, doesn't it? pH has to be greater than 1. What happens over here if pH actually equals 1? Then the sum of these two sides equals this side. Well, that can't happen because the straight line is the shortest distance from F to P. We're going from F to P in this very indirect route, and if this indirect route adds up to 4, the same as this direct route does, well, that's just can't happen. Not in this universe. So 1 is just not possible. It has to be greater than 1. That's a strict inequality. If it was greater than or equal, okay, but no, greater than. So this can't happen. The others could work. Here's one where they're showing you it takes 14 minutes to go from here to here the long way. 500 yards this way and 700 yards this way. How long would it take if you just went straight from here to here? And I guess we're just going to have to assume that you're going to walk about the same speed. Well, I think probably the first thing we need to do is figure out what your actual speed is. If you're covering this 500 and 700, that's 1,200 yards, right? So we've got yards. I want to figure out how many yards per minute we're covering here. So we got 1,200 yards over 14 minutes. So we figure out the speed at which we walk, and it's 85.7 yards per minute. So in 1 minute you walk a little less than a football field. Yeah, I suppose that's about right. Now what we need to know is how long this is before we can figure out how long it'll take us to walk it. And that, well, seems like a job for Pythagoras again. We got 5 times 100. As long as we're taking square roots, this can be an easier way to do it. Plus 7 times 100. We're going to square those. And then take the square root. And then it'll give us D, our actual distance from house to house. I separated things a little bit just to make them hopefully easier. Maybe write 5 times 100 for 500 and 7 times 100. That way we can just pull out the 100. If we got the same coefficient on each side, it's 100 squared times 5 squared plus 7 squared. This multiplication, so this is just 5 squared times 100 squared, 7 squared times 100 squared. We use our distributive property and write it this way. So we can just pull the 100 out now. The square root of 25 plus 49, which is 74. That whole thing turns out to be 860.2. Okay, that gives us this part right here. go straight from this house to this house at the same speed, which is 85.7 yards per minute. So we take our 860.2 yards and divide by 85.7 yards per minute. When I'm doing stuff like this, I always stick the units in. That way I can make sure that I've done it right. Because when you do this, the yards cancel. 1 over something in the denominator, you flip it and multiply, so that leaves you minutes up here in the numerator, and your answer is going to be in minutes, which is what we want. We don't want the answer in yards. We want the answer in minutes. And what does this turn out to be? Well, I get 10.03 something. So 10 is pretty darn close. I don't know what 3/100ths of a minute is. Probably not enough to worry about. So your answer would be C, which is 10 minutes. And if you notice, what you had to do was first figure out your speed. Then figure out the distance you were going to cover. Then divide the distance by the speed and get the time it will take you to cover that distance. Well, here we have our old right triangle, which is in a sense divided up by an altitude drawn from the hypotenuse to the right angle. Remember that? This altitude starts breaking things up. Now, one of the relationships we have is that, say, PR over PS is the same as PS over PQ. But that's not going to help us much because we don't have PR or PS. What else do we have? Well, we do have that QR over QS should be the same as QS over QP. Do we have that anywhere? QR over 15 would be the same as 15 over 7. QR over 50. Whoa, it's right there. And it looks like this is the right answer. What about this one here? Take 15 over QR. Okay, that's just the reverse of this. That equals QR over 8. Gee whiz, I don't see why that would be true. I don't even know where the 8 came from. 7 minus 15, I guess. I mean, 15 minus 7 would be 8. But that quantity has nothing to do with anything. QR minus 7 would give you PR. Maybe that's what whoever did it was thinking, but subtracting 7 from 15 gives you absolutely nothing. Oh, QR. Well, 15 squared plus 27 squared. Well, if we knew that SR was equal to 27, I suppose this would be correct. It's a kind of a more complicated way to do it, taking all these square roots. To figure out if this was right, you'd have to figure out SR. And for that, we'd probably have to figure out QR and then work backwards. We'd have QR and 15, then we could use Pythagoras' theorem and figure out if SR is really 27 or not. But I don't think we would have 27 unless we use this to get it. And QR over 7 is 7 over 15. Well, that just doesn't make any sense. That'd be this whole thing over this section of, in other words, this whole over the segment of the whole is the same as the segment over 15. That's you just got that all backwards and messed up. This is the right one here. I'm not even sure where this came from. Now for this one, they're telling us that the stitches are sewn along the black line segments 10 stitches per inch. We don't know how many stitches there are, so of course we need to figure out the length of all the stitches. First problem, for me anyway, is what it is they're calling the black line segments. I mean, this looks black. This looks kind of gray over here. These definitely look like stitches. Notice it's not a very even line, whereas these just don't look like they were stitches. So are they calling this cross piece, these cross pieces, black line segments also, and these, or is it just the square? I don't know. If this was a real test, I'd start throwing rocks at the guy who wrote it. But luckily, this is just for practice, so we can actually do it both ways if we want. So first thing we have to figure out is, let's figure out what the perimeter of this is. Looks to me like it's going to be a square, but let's find out. We've got all these hash marks in here giving us congruences. For instance, this must be the midpoint of this, etc., etc. So this equals this, and this must be 4 inches here. So these things are really easy. If we want to know these hypotenusae, this segment here is congruent to this segment here, and this is just half of the 8-inch segment. So this is 4 inches, this is 4 inches. What do we have? An isosceles right triangle. So the length of this is just the square root of 2 times either leg, or root 2 times 4 inches. That's the length of one of them. But there are 4 of those, so we can write that as root 2 times 16. Now, with 10 stitches per inch, the number of stitches, this is, I'm going to call this the L, the total length of stitched area, or the total length of stitched potholder, I guess. I don't know. Total length of the stitches anyway. What's the total number of the stitches? Well, it's going to be 10 times the number of inches, and this is in inches. So that's going to be root 2 times 160, because that's 16 times 10. 10 stitches per inch. That's the number of stitches. What's the square root of 2? It's about 1.41. So this is going to be close to 240 the way I did it. So they probably want us to add in the other segments too. Let's check. So these diagonals contribute 226.27 stitches. Well, that answer's not down there, so maybe they really meant us to include these black line segments also. Well, we know they're 4 inches each, and there are 4 of them. So that's another 16, remember, 4, another 16 total inches in length times 10, which is 160. So if we add that in, we get 386.27. Well, that answer is not down here either. Perhaps they're counting these as black line segments also. I mean, this is definitely black here. These are kind of light. I don't know what they're supposed to be, but if we count these as black line segments, we've got 4 more 8-inch segments. That's 32 inches. Times 10 would be another 320 stitches. Gives us 6. So I'm guessing this is the answer they're looking for. And when they say black line segments, I guess they were being totally literal. They meant all these borders here, these internal like crosshairs, and then all these diagonals. And if you add up all that, you get 70.6 inches. Although we were multiplying by 10 at each point. If we hadn't, we'd have just wound up with numbers that were, with all the decimals moved over 1 point to the left. Would have been 70.6 if we did it all the inches first and then multiplied by 10. I was doing it one step at a time to try to figure out what it was they were considering a black line segment. Judging from the answer that works, it must be pretty much everything you see that's black, I guess. They really meant us to take that literally. The one thing I know for sure is that this is the right way to do the problem. This is definitely the square root of 2 times this section here. And this section here is definitely 4 inches. These sides are definitely 8 inches. So all we had to do was figure out what it was one step at a time by adding them together, what it was they were considering black line segments. And it turns out it's everything. They were extremely literal. The correct answer is about 700. But as I say, the one thing I know for sure that is correct is that this is the square root of 2 times 4. This is 4. This is 8. How you interpret the rest of this, that's kind of irrelevant when you get right down to it. I mean, you can always add up numbers. If you know this is root 2 times 4, well, I think you can multiply that by 4 and get the whole thing. So in my opinion, the important part was recognizing you've got an isosceles right triangle. You can instantly compute these lengths. Then you just start adding things up. Now here's the kind of problem where if you try to absorb the whole thing at once and figure out how to do it all at once, your brain could melt down. Because it looks kind of messy, doesn't it? So just take it one step at a time. Don't be intimidated. What are they asking you here? The distance from A to B. Just this to here. Well, it looks to me like part of that we can get done right off the bat, because they tell us that the square has 4-inch sides. So the distance from here to here must be 4 inches. So we got that part. All we have to do is figure out what this is here. Well, this is an equilateral triangle. And what's really important for this line here is that this is also an isosceles triangle, which means that this line through the center here is bisecting this piece, and it's also bisecting the angle, and it's also a perpendicular bisector. All these things are true because this is at least isosceles. It's also equilateral, but the thing is, everything that's true for an isosceles triangle is certainly true for an equilateral triangle. So what we know, we'll just pick this one as an example. This side is 4, and this side is 2. But this is actually an hypotenuse, isn't it? 4. If we want to figure out what this altitude is here, now we've got a right triangle that's half of the original equilateral triangle with a leg 2, a leg we don't know, that's the one we're trying to find, and an hypotenuse. Or we've got 4 squared minus 2 squared equals, let's say that would be the altitude or the height of that triangle, right? So, but h is what we always use. It's too bad that hypotenuse and height start with the same letter. Let's try A. Okay, it's this distance here. We're going to say that's A, the altitude. Well, this is 16, and it's actually got to be the square root of that. Pardon me, that's important. Minus 4. square root of 12. That's about 3.6. So if we get 3.46 for this side here, pardon me, I shouldn't. It's a leg of this smaller right triangle. It's the altitude of this equilateral triangle, and what's really important is it is the direct length from A to this side. This is 4 inches. We just have to figure out what this is and double it so that we've got this plus this plus this. This is 3.46 times 2. That accounts for the 2 ends here, and then 4 is how far we traverse right there in the middle. And what does that turn out to be? And so this total distance turns out to be 10.92. So if you got 11, I'd say you were basically right. I mean, you could have just rounded this off to 3.5, doubled it, got 7, added it to 4, and got 11. I don't know. 10.9, this is round to the nearest tenth, so you're absolutely 100% totally correct answer would be 10.9. But if it was me, I'd give you full credit for 11. What's the big deal? Now remember, not remember, just take a good look. This is not a right triangle here, KLM. So the fact that we dropped an altitude here doesn't necessarily mean we've created similar triangles. This is different. But we have created 2 right triangles. That's probably the important part. If we find LN, which we can definitely do because we have these 2 right here, this leg and this hypotenuse, then we'll have a leg and hypotenuse over here, and we can find this distance, and that'll give us the whole thing. Suppose we didn't want to use Pythagoras' theorem. After all, it is kind of lead to long, clumsy equations with lots of squares and square roots and stuff. What else could we do? Well, we know about inverse trig functions. And we also know that the cosine of this angle would be adjacent over hypotenuse. Remember? The sine, some old hippie, that's opposite over hypotenuse. Cosine, got another hippie, adjacent over hypotenuse. So, that might be a less messy way to do it. Let's try. And let's call this alpha. We've never done that before, right? So we have that the cosine of alpha equals 11 over 12. Why does that matter? Because if we take the inverse cosine of 11 over 12, we'll get the angle. When we've got the angle, we can use that to find ln. And it's supposed to be the inverse cosine, pardon me. And so to get our angle, we divide 11 by 12. And then we have to take the arc cosine of that, pardon me, the inverse cosine, and get 23.56. It's around that. 23.56. That's alpha. Now that we know alpha, we can easily get this, because cosine of 23.56 degrees equals ln, that's opposite, over 12, or ln equals 12 times the cosine of 23.56. But now here's the funny part. Did we really need this? After all, we already know what the cosine of alpha is, don't we? It's 11 over 12. And the answer is yes, we did need this, because what we're using down here for ln is the sine, not the cosine of 23.56. So we had to find the angle first, then we could find the sine, and multiply it by 12, and that'll give us ln. And remember, the sine is always less than 1, so when you're multiplying by these sines or cosines, you're always going to get a number smaller than what you started with. And let's try it. 23.56. Yeah, let's see here. If I can put that in memory. There we go. 12 times. What was that, about 4.8? Yeah, I'll call it 4.8. Why not? So if this is 4.8, now let's do it the other way. See which one you think is easier. Over here we had two lengths, the sides we had a leg and a hypotenuse. We found the angle and then used the sine to get this one. We could also use Pythagoras' theorem, that this squared minus this squared will be this squared. Or, let me write that down so it actually makes a little bit of sense. Minus 4.8 squared should equal nm squared. And if we use Pythagoras' theorem, we get this equation here. It's square root of 81 minus 23 is what would be nm, which turns out to be 7.6. Well, we got 11 here, so we just have to add 11 and get 18.6. Oops. Well, that doesn't look much like a 6 to me. There we go. 18.6 would be the length from here to here. That's km. You can decide what you like better. We used trig functions over here to get that this was 4.8. We could have done the same thing here. We could have said that the sine of this angle is 4.8 over 9. We found this angle, and then when we find that, we'll just do what we did before, except that we flip things around a little bit, and this will be the cosine of this angle multiplied by 9 will give us this leg here. Either way we do it, we had best to get 7.6. I just did it two different ways so that you can see. Did I mention this before? There's more than one way to solve a math problem. Just do whatever works easiest. I think I've mentioned before that the easiest way is probably the right way and the one that will get you the most credit. In math classes anyway. I don't know about history. Couldn't tell you. Well, this is funny, because I don't know if they actually, I'm never sure. They say, I don't like this to explain how. It seems to me, if you can explain how to do it, then you know how to do it. If you know how to do it, then why not just do it? If you do it and get the right answer, that is the explanation. At least that's the way I've always looked at it. But then what do I know? How would you do this? How would I do it? Well, I'll tell you what I would do. First, I would find x. How? Well, all you have to do is find this. This is the hypotenuse of this right triangle. and you got 4 of those. So you would multiply by 4. Once you had this, well, finding this first definitely works. But when you've got this, you still don't know what these two are, and you don't know this angle or this angle. Do you? Well, maybe we do. Suppose we extend these up and up and up and up, but not to the stratosphere, just to the top step. What is this vertical distance from here to here? Well, I'd say it would be the same as z, wouldn't it? But it would also be this step plus this step plus this step plus this step. They tell us they're congruent. So this must be 8, 16, 24, and 32. So this one's 32. What about this here? Well, the length from here to here is the same as the distance from here to here, right? Because when I draw these lines in here, I'm basically finishing off a rectangle. And these little steps in here tell me what the measure of these sides of the rectangle are. If I add these up, I get 11, 22, 33, and then 44. So I get 44 down here. The only one that really requires much computation would be this one. That's 8 squared plus 11 squared is 64 plus 122, and then we'll take the square root of that. And that will give us 1/4 of x, won't it? Pardon me. X squared over 4. No, I had it right the first time, pardon me. If we take the square root, that gives us x, almost x, that gives us 1/4 of the total distance of x. And what is 64 and 122? So according to my calculator, the square root here is equal to 13.6 inches. And that's x over 4. So if we want x, we just have to take 4 times 13.6. Because, in other words, 4 times each of these hypotenuses. And so up here I would get 54.4. So the only one that really involved much computation was this one here, where we had to actually use Pythagoras' theorem to get this one small diagonal. The rest of it was pretty much just simple addition. Now this one, first thing we have to do is interpret what in the world it is they're asking us. They say that they drive due north from Dalton to Bristol. Doesn't look due north to me, but if they say so, we'll stick with that. And then they go from Bristol to Hilldale. And they're giving us all these dimensions, which helps a lot, because they're asking us if we went due west from here to here. All we know is that this is due north. If this was due west, then this would be a right angle. Maybe I should put a little question mark next to it, because we don't know that it is a right angle. In fact, I don't even know if that's a question mark. It's supposed to be. How do we know if this is a right angle? Well, we have all the dimensions, and we have Pythagoras' theorem, which goes both ways. If this squared plus this squared equals this squared, we have a right triangle. And conversely, if we have a right triangle, then this squared plus this squared will equal this squared. Well, this time we want to know if we have a right triangle. So what we have to do is square these two, add them up, and see if it equals this squared. That shouldn't be too hard because squaring 100 is going to be pretty easy. That's just, what, 10,000? And the question is, does that equal 71 squared plus 74 squared? That's one way we could do it. Let's see what happens if we try that. Well, if we actually perform this, 71 squared is 5,041. 74 squared is 5,476. Well, you don't even have to add these up. 5,000 plus 5,000 is 10,000. This is not going to add up to 10,000, so we don't have a right triangle. You could actually use some trig or something to figure out what this angle was, but they didn't ask us that, and there's no reason to go crazy figuring out all kinds of information they didn't ask for. If you see this on a test, the answer is no, and this is a totally acceptable reason why the answer is no. This whole thing can't be a right triangle because this is not a right angle. And we can easily prove that using the converse of Pythagoras' theorem. Now here they're going to ask us some questions about a water ride. They want to know how high is the ride above point D. And they've got it fairly well laid out for us here. We know the angle. We know the horizontal distance. So, suppose we wrote tangent of 35 degrees equals tripping on acid. Tangent. Opposite over adjacent. So that's BD over 50. Or BD equals 50 times the tangent of 35 degrees. So if we take the tangent of 35 degrees here, we're going to get 0.7 times 50 is 35. That means the altitude here, that's 35. We'll just go ahead and write it in, I guess. Or maybe we can put it up here. Now what they want us to find is the total distance. We go up all the way to B and then down to C, and what would the total distance traveled be? Well, I think we can use Pythagoras' theorem to find both A and B, I think. Well, of course we can. That's definitely true. Is that the fastest way? We'll see. Yeah, let's try it and see what happens. For this, the thing is, we know this angle here. So, if we know angles, we hardly ever have to use Pythagoras' theorem. That's the whole point of trigonometry, when you get right down to it. So we could use the cosine or the sine here. It's up to you. Remember, sine, some old hippie, opposite over hypotenuse. And AB is what we're looking for. So we could write that the sine of 35 degrees equals 35 over AB. And that should give us that AB is 35 divided by the sine of 35 degrees. Let's see how that works out. If I punch in 35 here, take the sign, I get 35 over, what was that again? 0.57. And when I work this out, I get 61.4 for AB. Now this one, we don't have any angles, so Pythagoras' theorem might actually be a good way to go here. So what does that give us? It gives us 35 squared plus 42 squared would equal BC squared. Why am I doing that? Well, we're going to find AB, we just did, and then BC. And then we're going to add them together. Now this now, if we use Pythagoras' theorem here, 35 squared plus 42 squared is the same as, well, this implies that the square root of 1225 plus 1764 is BC. That's the square root of 2989, or 54.7. If we add these two up, we get 116. So our answer, how far above ground does this ride get? 35 feet. Total distance covered, 116 feet. This one, I think it's easier to go ahead and use the sine or the cosine and get this. Or, yeah, that over here, since we didn't actually have any angles, then I just went ahead and used Pythagoras' theorem. But normally if I've got an angle, that's what trig functions are all about. If you got angles, then go ahead and use them if there's a way to do it. Now remember a while ago, knowing all three sides of a triangle, we were able to compute this altitude. And if we can do that knowing all three sides of a triangle, once we've got the altitude, then we can compute the area, which means that all we have to know is all three sides of a triangle, and we can compute the area. And Heron, he incorporated that. He used the fact that given all three sides, we can find the altitude, and then just buried that formula inside the area formula. In other words, the 1/2 BH, he replaced the formula for H with H in the 1/2 BH. I can write it this way up here. We get 1/2 BH. Well, if we know all the sides, we can use a sort of complicated formula to find H. Well, he just substituted that complicated formula in here and did a bunch of rearrangements and came up with this, which is not a simple expression, but it's good for theoretical work because it shows that if you have three sides of a triangle, you can in fact find the area. So what is it they're asking us to do here? We have EF equals FG, okay, and that's 15. And EG, this is bottom one here, they say is 18. Well, they gave us an equilateral triangle. That might help. Use Heron's formula to find the area. Okay. Well, the first thing we're going to do to make this halfway reasonable is notice that if we know these three sides, this S here, which is not a simple expression at all, is just a number. It's just 15 plus 15 plus 18. And I think that works out to 48, which divided by 2 is 24. So we can replace S with 24 all the way through here. And that's a lot easier than replacing it with this big thing here. So that's one thing we can do. In fact, why don't we do that? Okay, there's our first s, 24. I'm not going to put the square root symbol in until we're all done. It makes me feel cramped. 24 minus EF. What's EF? It's 15. Times, and here we go again, 24 minus FG, which is 15 again. And the last one is 24 minus 18. And that's the whole thing. And we're going to take the square root of that. I'm hoping that you have at least seen this. It's a much easier way to write a square root. To the 1/2 power. You know how to square things and cube things. And you know that something like x to the minus 1 power means 1 over x. Well, x to the 1/2 power is square root of x. Okay? When you've got long expressions like this, it's usually easier to put them in parentheses and just write the 1/2 up there as an exponent. Well, this looks like a job for Mr. Calculator. And 24 minus 15 is 9. 24 minus 18 is 6. So we got 24 times 9 times 9 times 6. Well, if we do all this and take the square root, I get 108 for the area using Heron's formula. Now let's try it this way. In order to do that, we have to find h. Well, we can do that because this is particularly easy because we have an isosceles triangle, which means that our altitude is also an angle bisector, and it also bisects EG. The short version of that is this is 9 over here. So now we can use Pythagoras' theorem to find this leg. We've got a hypotenuse of 15, a leg of 9, and we just have to find this leg right here. So first thing we need is a little bit of room to work, right? Let me draw a line under this. It doesn't look like anything. Now, we're doing part B. And we should have that 15 squared minus 9 squared will give us our altitude squared. Let's see here. That's 225. Minus 81. Well, I get that a squared is 144, so we must have that a equals 12. That's the height. Now we're going to use 1/2 BH. Heck, why don't I just write it here? 1/2 B, which is 18, and the height, the altitude we figured out, is 12. And of course, if you just do your division right here, you get half of 18 is 9, and 9 times 12, well, we know that's 108. Well, that looks a lot like this, doesn't it? Turns out good old Heron had it right. Assuming that 1/2 BH is correct, then Heron worked out a correct formula. Yeah, pretty smart guy, huh? Now the last thing they would like us to do is to use Heron's formula to show that the area of an equilateral triangle is equal to this, where x is the length of one side. So I went ahead and put in an equilateral triangle here just to give us an idea of what we're looking at. And we have, for the area we have to figure out this altitude normally, but with Heron's formula we don't. We've got this, and with every side equal to x, let's compute some things here first. What is s equal to? If every one of these is equal to x, that's 3x divided by 2. So 3/2 x, would be s. We got x plus x plus x, because 3 divided by 2. So 3/2 x equals s. That's good. And each of these here equals x. So let's write it out. Well, it's kind of boring, but I went ahead and wrote it all out, even though every one of these expressions is exactly the same, isn't it? That stands to reason, because s is the same all the way through here, and we have an equilateral triangle, so every one of these sides is the same. So every one of these expressions is exactly the same, and every one of these expressions works out to be x over 2, right? And that's x over 2 times x over 2 times x over 2. So I'm going to call that x over 2 cubed. And that's just these three right here. These multiply out to x over 2 cubed. And that is, but we have to multiply that by 3/2 x. Okay. Boy, that's bad. Let me try again. 3/2 x. There we go. And remember, we need the square root of this, whatever this turns out to be. Yeah, that's 3/2 x times x cubed over 2 cubed, which is 8. And we're going to need to take the square root of that. Well, this is x to the 4th. And this is going to be 2 times 8, which is 16. So what we have is 3 times x to the 4th over 16, and we want the square root of all that. Well, the square root of this part, x to the 4th over 16, that's easy. That's just going to be x squared over 4, right? You square x squared over 4 and you get x to the 4th over 16. And this just becomes the square root of 3. That's what we get for an area for an equilateral triangle using Heron's formula. How does that compare to, well, looks like the same thing to me, except they put the root 3 on the right hand side and I put it on the left hand side. But it looks like exactly the same formula. They said justify. Well, I think we just did justify it. We didn't just justify it, we algebraically proved that this is in fact the area of an equilateral triangle with one side length equal to x. Well, that's about it for the review.